And just when you thought Kukla would forget about position, velocity, and acceleration, here we are again. Assignment 41 has as its focus the relationships between those things. Okay, and we should probably review that S prime. Now let's go back even further. Position with respect to time is usually S of t or x of t, not x of x, but x of t. The rate of change in position with respect to time is a change in s over a change in t, and so that's going to be ds dt, which we call velocity. Velocity is the derivative of position. If we're talking about average velocity, we do on A to B, we do S of B minus S of A over B minus A. But if we want instantaneous velocity at time equal to c, that's v of c or s prime of c, or if you wanted limit notation as x approaches c, of s of t minus s of c over t minus c. So we could use our limit definition of the derivative to find slope at one point on position, and that slope on position is going to be velocity. Remember also, we said that speed is the absolute value of velocity, and then we came to acceleration. Acceleration is the rate of change in velocity with respect to time, and so we could say a of t equals v prime of t. But since v is the derivative or rate of change in position with respect to time, we could say that this is also equal to s double prime of t. Thus, acceleration is the rate of change in the rate of change in position with respect to time. Okay, so now how would I find average acceleration? Well, on A to B. That's where I use V of B minus V of A over B minus A. But if I'm looking for acceleration at t equals c, then that's v prime of c is a of c. I guess it could also be s double prime of c. Okay? All right. So now what are we going to do about this? Well, now I want to say find the instantaneous rate of change and in each situation. And so instantaneous rate of change, and we need a different color for this. in the area of a circle when r equals 5. Okay, so I know the formula for area of a circle is pi r squared. So I've got here area as a function of r. And I want to know the instantaneous rate of change in area. So I'm looking for a prime of r, and really when r is 5. That's what I'm looking for here. So let's start by saying, okay, let's take the derivative of both sides with respect to r. On the left-hand side, I have dA dr, or a prime. And on the right-hand side, that's a constant. The 2 comes down, right, because I have a constant times a function. Take the derivative of the function and multiply it by the constant. And I get this. Isn't that freaky? That's circumference. Circumference is the derivative of area. Very freaky. Okay, and what did we want? We wanted the instantaneous rate of change in area when r is 5. So we want a prime of 5. And so we're going to get 2 pi times 5, or 10 pi. 10 pi is our instantaneous rate of change in area with respect to radius. All right, so what about find the instantaneous rate of change in circumference of a circle when r equals 5. Okay, so what's the formula for circumference of a circle? We know that the circumference of a circle, C equals 2 pi r. And what is it that we're looking for? We're looking for the instantaneous rate of change. So we want to take the derivative of both sides with respect to r. On the left, we have dc dr, also known as c prime. And on the right, the derivative of a constant times r to the first is just that constant. So it doesn't matter that we're at r equal 5. The rate of change in circumference with respect to radius is always 2 pi. How about find the instantaneous rate of change in area of a circle when circumference is 8? Well, that's a little more challenging, isn't it? Because in this situation, I am asked to deal with this, because my input of 8 for a prime is a c value. So how do I write area as a function of circumference? Well, I know circumference is 2 pi r, and I know area is pi r squared. I'd like to get rid of this r and replace it with some c stuff. Well, this is my helping equation. I want to solve that equation for r. So c over 2 pi equals r. Then I can replace this r here with c over 2 pi. So what do I get then? I get area equals pi c over 2 pi squared. Now area isn't a function of radius, it's a function of circumference. So we get pi over c squared over 4 pi squared, right? Because not just squaring that, but squaring this and squaring this. So we can cancel here, and so area as a function of circumference will be c squared over 4 pi. Now, I have a lot of students who want to use quotient rule here. But remember, your middle school math teacher said this can be written like that. Much easier than using the quotient rule here is just to realize that you're looking at a constant times the function. And so when you take the derivative of that function, you're going to have 2c times that constant. 1 over 4 pi times 2c. The 2's cancel, and we get c over 2 pi. And that's a prime of c. We want a prime of 8. So we're going to put an 8 in for c, 2 pi. And so 4 over pi is a prime of 8. Okie doke. All right. How about this one? Find the instantaneous rate of change in the volume of a sphere when radius is 2. Well, I need the formula for volume of a sphere. And if you don't know the formula of volume of a sphere, you actually do need to know it. So go to that page in your notes called Formulas That I've Forgotten That I Really Need to Remember, and write this down. Volume of a sphere is 4/3 pi r squared. Okay, and we're looking for the instantaneous rate of change in volume with respect to radius. Oops, careful. 4/3 pi r cubed. It's volume. It's got to be cubed. Okay, so then I'm going to have dv dr, which you might want to call v prime. And over here, I'm going to bring down that 3. 4/3 times 3 pi r and subtract 1. Well, these cancel, and I get 4 pi r squared. Do you remember where 4 pi r squared comes from? Well, that's the formula for surface area of a sphere. Isn't that interesting? The derivative of area of a circle is circumference, and the derivative of volume of a sphere is surface area of a sphere. I find that very interesting. We're not quite done yet. We want v prime of 2, and so 4 pi times 2 squared, or 16 pi, is our instantaneous rate of change in volume of a sphere when radius is 2. Okay, how about this one? How about find the instantaneous rate of change in the volume of a cylinder whose radius is a constant when height equals 5. Okay, well, again, I'm going to have to start off with the formula for volume of a cylinder, which we're all supposed to know, and if you don't know it, please write it in your notes because I'm not giving it to you on a test. Pi r squared h. Now, we said r was a constant, so all of this is some constant. So when I think about taking the derivative to find the instantaneous rate of change in volume, I'm taking the derivative with respect to height on both sides. So over here, I have dv dh, or v prime, and over here, this is a constant times a function, and I'm taking the derivative of that function. The derivative of h with respect to h is 1. And the derivative of a constant times a function is the derivative of that function times the constant. Okay, so the derivative of volume of a cylinder when radius is constant is the area of a circle formula. That's just so nifty. And we want v prime of 5. But wait, that's an h value. Well, I don't have an h, Mr. Cooper. I know. I know. So v prime of 5 is simply going to be pi r squared. There's no place to plug that h in. All right, so that's the first thing. Next, Oh, I meant to say, we talked about average rates of change and instantaneous rate of change and position, velocity, acceleration, speed. But one thing we didn't do was displacement. Displacement is a change in position. That's what displacement is. Okay? All right. Next, I'd like to look at three situations. The first one has a thrown rock. And the height of the rock, the position of the rock, is given by S of t minus 4.9 t squared plus 24t. Okay, there's our position as a function of time, and I'm asked to find v of t and a of t. Well, we know that v of t equals s prime. And so I'm going to take the derivative of this and have negative 9.8 t plus 24. And a of t is v prime or s double prime. So if I take the derivative of this velocity equation, I've got a of t. And notice this negative 4.9 is gravity. Is gravity on Earth in meters per second per second. So what have we found here? Well, acceleration due to gravity is negative 9.8 meters per second. Actually, this is coming from 1/2 at squared plus v sub o t plus s sub o. So this number that I'm looking at, this 4.9, is actually half of acceleration due to gravity. That's where that number is coming from. Okay, so acceleration in this case is a constant. Velocity is this linear function with a negative slope, and that makes sense to me because this object has fallen to the ground. Okay, now we found those things. What about v of 2 and a of 2? Well, v of 2, I plug a 2 into velocity, and I'm going to get v of 2 will be negative 9.8 times 2 plus 24. So that's negative 19.6 plus 24 equals 4.4. Yeah. And I don't have any units here yet. I don't see any units given to me. I know that this is metric, so and I believe time is in seconds, so this would be meters per second. Okay. Now, what about finding a of 2? Well, a of 2 is negative 9.8 meters per second per second. Okay, that's a of 2. And since this is a constant, at any time, I'm going to get that constant. And that's the cool thing about living on a planet with gravity. Acceleration due to gravity will always be a constant. It will always be the same. It doesn't matter if I'm at your house or my house. Gravity is always going to be the same. Now, that is to say that if we go up really high on a mountain, not even Mount Everest, you might notice, no, you wouldn't notice, but you could measure a very slight change in gravity. But for the most part, we say that's gravity due, acceleration due to gravity. Okay, C. How long until the rock is at its maximum height? Well, we have this equation, S of t equals negative 4.9 t squared plus 24. And what I want to say is that in pre-cal, probably even in Algebra 2, we could find the max of this down-pointing parabola by using negative b over 2a to find that time when the maximum occurred. And so we'd have negative 24 over 2 times negative 4.9. And so we'd have negative 24 over negative 9.8. And so we could find time that way. Well, yes, you can do it that way, but this is calculus. And so this is our position function, st. When is the rock at its maximum height? Here. What do you notice about the slope at that point? The slope equals 0. So the derivative will equal 0. What was our derivative? Our derivative was negative 9.8 t plus 24. And I want to set that derivative equal to 0. Well, look what happens. I get 9.8t equals 24. And when I divide both sides by 9.8, why, that's the same as I found with my Algebra 2 skills. So I can find the time when the rock reaches its maximum height by finding when the derivative of position is equal to 0. Now, if I want to know what the maximum height is, I got to take this value and plug it into not velocity, because if I do, I'll get a 0, because the slope here is 0. But instead, if I want to know the maximum height, I have to plug this number into the position equation. So 24 over 9.8 equals negative 4.9 t squared plus 24t. So I have to take this and plug it into both of these. You know, I would probably say, why don't we use our calculator for this? Y equals negative 4.9 x squared minus plus 24x. And if I go over to the table, I can type in 24 divided by 9.8, and I get the height at that moment in time is going to be 29.388 meters. Okay. And remember, we started at 24. Did we start? No, we started on the ground. Sorry, position at 0 is 0. Okay. What's next? How long to reach 18 meters? How long to reach 18 meters? Well, the height is 18 meters. That's when does S equal 18? Well, let's plug in 18. And I could subtract this from both sides. I wouldn't be able to factor that, but I could use quadratic formula. But since we've already had the calculator out on this problem, why don't we see where these two graphs intersect? So I've got position in there. Let's have 18 in there. And now let's think about our viewing window. This was 24 over 9.8. And that's between 2 and 3. And when does this happen? At 24 divided by 4.9. Okay, so what does that tell me? Well, it tells me that I don't need any negatives here. 10 is plenty, because 24 divided by 5 is going to be 5-ish, so I could really cut that back, maybe 7. And then my y values, I'm starting from the ground, so I don't need negative numbers. And I'm only going up to this number, so I think 4 or 5 should be plenty. Graph. Well, the height was oh, we know the max height is already 29 point something. Silly me. So let's go with 35. What? Wait, what did I change? Oh, it didn't change to, so 35 goes there, and graph. Okay, so now I see my position function, and I wonder, when does position equal 18 meters? So y equals 18. So if I graph y equals 18, that's where I put the 35. I can see that the rock is going to be at 18 meters, once on the way up to 29 point something and once on the way down. We can do second, calculate, intersect to find these points of intersection. So the second time will be at 3.973 seconds, and the first time will be, let's bring that cursor close to the first point so the calculator doesn't get confused, and find the second point again. 1, 2, 3. And I find the first point here is 0.925 seconds. So these are the two times when the height will be 18. I need the position function here in this problem because they gave me a height. Okay. And what's the next question? How fast is the rock going when it's at 6 meters high? Well, so I saw before a position function 6 feet high, and what I'm wondering about is, how fast is the rock going? Well, how fast is actually asking me about velocity. So I'm looking for v, and I don't know the time. So first I have to find the time when s equals 6. So let's find the time when s equals 6 by graphing on our calculator. Second, calculate, intersect. Enter, 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 and I get 0.264 seconds. All right, so then I want v of 0.264 seconds. Well, how can I do that? I'm going to plug that velocity at that time into the velocity formula. And remember, the velocity formula was this. Again, this is decimally. I don't really want to plug it in here by hand. So I'm going to go over here, and in y3, I'm going to do negative 9.8 t plus 24. And then I can go over to my table and type in 0.264. And I get the number. Sorry, can't see it with all the glare. 5.995. 995, and velocity would be meters per second. Now, notice that this is a positive number because the slope here is positive. Over here, I have a negative number, or I should have, because I see a negative slope. Will you please find out how fast the rock is going the second time the rock is 6 meters tall? How will you do that? Yeah, so I need to find this time when position equals 6 meters. Whatever that time is, I'm going to plug into velocity. So I'm going to go back to graphing my position equation with the line y equals 6, and I'm going to do second, calculate, intersect for this point over here. enter, enter, enter. And so now I'm looking for velocity at 4.63 4.634. Okay, and then I'll use my table feature with velocity to find velocity at that time. Do I have something turned off here? How can that be always? Oh, I'm looking for Y4. Oh, that might change this one. So where's Y4? Oh, there it is. Yep. This is 21.413 meters per second. And now if I type in 4.634, I end up with negative 21.413. Oh, isn't that interesting? It's almost as though there's an axis of symmetry running through this, so that this is a reflection of that, and so that this positive slope would have a corresponding negative slope on that same symmetric point. Okay, nice. Okay, example 2. So, example 2 says s of t equals negative 16t squared plus 80t plus 96. By the way, I could always factor t squared minus 5t minus 6. Okay, there's my s of t function. We know velocity is going to be the derivative of that. And we know that acceleration is going to be the derivative of that. And this, because I see that negative 32, I know I'm talking about feet. This is feet per second. This is feet, and this is feet per second per second. Okay, so I've got position, velocity, acceleration, and now they're going to ask me some questions, and I'm going to have to figure out which of these to use. I might have to use some combination of them as well. The first question says, how fast was this object going when it hit the ground? I mean, we know at time equal to 0, this is at 96 feet. So my object goes up and comes down, and I want to know how fast is it going when it hits the ground. And some students like to say, well, it's not moving when it hits the ground, and so its velocity is 0. But actually, I want the velocity at the time of impact, not after it hit the ground, when velocity would be 0, but instead actually finding velocity at that moment in time. The only problem is I don't know that moment in time. But I do know the height at that point. What's the height at that point? Well, the height at that point is 0. So if I set my equation for position equal to 0, and then divide both sides by negative 16, I get something that I can factor. And so I see that t equals 6 or t equals negative 1. Well, we can't have negative time, so that's when, at time equal to 6 seconds, this object has hit the ground. But they didn't ask me when this object hit the ground, they asked me how fast it was going. So I need to use velocity. V of t, negative 32t plus 80. And v of 6 then is negative 32 times 6 plus 80. So negative 192 plus 80 is going to be negative 112 feet per second. That's going very fast. Okay, what else do they ask us? Max height. Find when the max height occurs. Okay, so we had s of t equals negative 16t squared plus 80t plus 96. And v of t then was negative 32t plus 80. Now, max height for this down-pointing parabola occurs here. And what we know about the slope, or rate of change at that point, is the slope of position at this point is 0. Well, it just so happens that v's other name is the slope of position. So if I set the slope of position, or velocity, equal to 0, I can find out when the maximum height occurs. So I'm going to add 32t to both sides. And so t equals 80 over 32. I can take an 8 out of each of those, and I get 10 over 4 with 5/2 seconds to reach max height. Okay, what else? How about average? No. When is the rock moving the fastest or the slowest? Now, an interesting thing is about slope. When I think about this position function for this problem, position function looks like this. I know that the change in position with respect to time, or the slope on this graph, is velocity. So when the rock is moving fastest, I'm looking for when velocity is largest. Okay, so not here. That's when height or position has a maximum. I want to know when velocity has a maximum. Well, velocity being slope, I'm looking for the most positive slope. And if we think about our v function, remember v was negative 9.8 t plus 24. That function looks like this. So 0, 24, and over here we have 24 over 9.8. This is our velocity graph. If I want to know when the rock is moving fastest, I look for the highest point on the velocity graph. Well, that occurs here at t equals 0. And how fast are we going at t equals 0? Well, if I plug a 0 in there, I get 24. And so, when is the rock traveling fastest? At t equals 0. The rock is traveling 24 feet per second. Okay, but what about slowest? Well, slowest is an interesting word. When I think about slowest, I think about slope equal to 0. Because over here, when I have this very negative slope, I don't think a negative slope is the object moving slowly. This is moving very fast down. Positive slope told me the object was still moving up. 0 slope tells me that the object is neither moving up nor down anymore, but these negative slopes, they tell me that the object is moving down. And so this slope over here, at this moment in time, when I take this moment in time and I plug that in for t over here, I'm going to get a very negative number. So, yeah, I guess I really want to say I really want to say when v equals 0, and that happens at t equals, what was this point? 24 over 9.8 seconds. That's when we have, when we're moving slowest, because we're not moving at all. I guess you could ask the more precise question, when is it moving down fastest? And that would be here when it hits the ground. And I think we already figured out when it hits the ground. Okay. Can we find average velocity? On 0 to 3? Well, so I want to caution you about this, because even though I've said it now in at least 2, if not 3 videos, average velocity is not v of 3 minus v of 0 over 3 minus 0. That's average acceleration on 0 to 3. If I want average velocity, I need to do s of 3 minus s of 0 over 3 minus 0. I want the displacement divided by the amount of time it takes to have that displacement. Okay, so I'll pull out my calculator. I've got my s function already typed into y1. And so if I typed in 3, that's going to be 27.9. And if I plug in a 0, that's 24, isn't it? If I plug in a 0, no, that's 0. Because this thing, oh no, we're doing example 2. Yes, that's s of 0, position of 0 is 96 over 3. Okay, so 27.9 minus 96, not there. 27.9 minus 96 divided by 3, and I get negative 22.7 feet per second per second. Remember, these are feet per second. No, we're doing average velocity, silly. Sorry, just feet per second. These are feet on top, these are seconds on the bottom, so I get negative 22.7 feet per second. Negative tells me that I'm moving down. Okay. Last problem I'm going to look at with you is this interesting one. This is an interesting position function because it's not Newton's falling object. 13t squared plus 52t minus 60. So, you know, v of t then would be what? That's right, I bring the 3 down, I subtract 1, bring the 2 down, and take the derivative of 52t to get 52. And then acceleration would be 9t minus 26. Okay, so when does the object, I'll let you fill in it now, change direction? Well, that's kind of hard to say using the position graph, because I'm going to get a third-degree polynomial with a positive leading coefficient. It's going to look like this, and this is where I stop going to the right and start going to the left, or I stop going to the left and start going to the right. So I'm looking for these places, which is kind of hard to do with position. With velocity, I see the slopes of position are equal to 0, so all I need to do is set velocity equal to 0. So the object changes direction when velocity equals 0. Okay, so how do I solve this? I don't really want to factor that. So I'm pulling up my calculator, and I'm typing into y1 3x squared minus 26x plus 52. We don't need these other things, right? Okay, so I want to know when this function equals 0. Well, I think I need to change my viewing window. How about my y values go to negative 20? In steps of 5. Aha! Here's a place where velocity is 0. Here's a place where velocity is 0. Second, calculate 0. So bring my cursor to the left of that x-intercept and hit enter, to the right of that x-intercept and hit enter a third time, and so I get at t equals 3.131 seconds, and t equals, second calculate intercept, 1, 2, 3, I get 4.617 seconds. Okay, so at these two times, the object changes direction. If we look at this position function, I'm moving to the right, I'm moving to the right, I stop moving to the right, I move to the left, move to the left, stop moving to the left, move to the right, move to the right. So this is 3.131, and this is 4.617. So at those moments in time, the object changes direction. You know, I could also do that by thinking about velocity. 3.131, 4.617. Here's my velocity number line. And what I know is velocity is always positive until this point. After this point, I have a negative velocity. See all those negative slopes? And then after this point, I have positive slopes again. And so I can see when my velocity goes from positive to negative or from negative to positive, what that looks like on the position graph is I'm changing directions. Okay? All right. We did that. How about when is the object slowing down? When is the object slowing down? Well, I think I want to think about slowing down as velocity decreasing. So let's think about that velocity equation again. V of t equals 3t squared minus 26t plus 52. So this is a parabola, and I want to know when this parabola is decreasing. You know, decreasing means has a negative slope. Velocity has a negative slope. Well, if I look at my velocity graph looks like this. And I see all these negative slopes. Okay? So, slowing down, slowing down, slowing down. When is the object slowing down? From from 0 to whatever time this is. Now that time is when the slope of velocity is 0. Hey, isn't that acceleration? A of t equals 6t minus 26. And we want to know when the slope on this velocity curve, also known as acceleration, equals 0. So this point here will be 26 over 6, or 13 over 3. At t equals 13 over 3, the object stops moving and changes direction, but that stops moving. At this point, we're moving. This is the moment in time where we're moving to the left fastest. Okay. It's the most negative velocity on the graph. I'm looking for wherever I have negative slopes to say the object is slowing down. The object is slowing down when velocity is decreasing. Velocity is decreasing on 0 to 13/3 seconds. So I want to do that. Okay? All right, well, there's a lot of thinking to be done in these problems, and I noticed that that thinking isn't really calculus thinking because it's pretty easy once you've been given a position function to then write the velocity and acceleration functions. What is challenging is trying to figure out, should I be using position, velocity, acceleration, or some combination of those formulas? All right, well, have at that homework. I hope this video helps you with that, and I look forward to your questions in our Zooms and on the GroupMe.